Last week's problem of the week, we solved this problem with an Atwood machine that kind of turned into a constant acceleration problem and a projectile motion problem. And we got a final y max, the final height that the small mass goes. This time we're going to solve this with energy instead. So we have two objects. I'll do it over here. We have two objects. I'll do it in blue. And we'll take we'll take the ground, the actual ground as the y. So here, I'll draw another little sketch. This is m. This is little m. Their tensions are happening. And then the ground is down here. And we'll take that to be our y equals 0. So that means that they each start a distance h off of that ground. So initially they look like this, and then afterwards big M has fallen down to the ground and little m has gone up. And we're going to just first take, before it scrunches the tension, the rope. So before it scrunches, it's just gone up a distance h, just like big M has gone down a distance h. So here, if this is our 1 and this is our 2 for our energy problem, then y here would be 2h for this little m guy. All right. And then we can solve for whatever velocity this is that it has, right? And big M is going to have some velocity too. I mean, it hits the ground and then eventually it rests on the ground, but that very moment, right when it hits, it has some velocity. So initially, we have no kinetic energy. We just have mgh for gravitational potential energy plus little m g h. So two gravitational potential energies here, right? Then we have big M falling down to the ground, and it's going to have some kinetic energy. So 1/2 big M v squared. Since we are ending this energy analysis right when the mass hits the ground, the velocities will be the same between the two masses. They're connected together. The rope hasn't scrunched yet. So we will also have velocity 1/2 little m v squared for the other guy, kinetic energy. And then we have big M is at 0 gravitational potential energy, but little m is at 2 mgh, right? mg 2h, in other words. Okay, and we have h, we have both masses, and we can solve for the final velocity. So we have gh m plus m here. Oh, and in fact, this guy on the right is going to cancel out and make this a minus here. So that takes care of all those terms. And then we could, say we bring over the halves over to the other side. And if we wanted to just solve it all the way for v squared, we would have pulled out a v from these two terms on the right, and you get big M plus little m. All right, so that's fantastic. You'll notice that ought to be the same final velocity that we got before here, 2gh big M minus little m over big M plus little m, which is a lot easier. So if you can use energy, do use energy. This problem was from chapter 5, so I set off solving it using dynamics and then later realized that this can totally be done with energy. So it's a good use case for showing how much easier that can be. And we don't even have to then take that and finish the problem the same way. We can do that if we want, but we can keep using energy. So now let's take our moment 1 and moment 2 but with energy. So moment 1 we'll say is just the same as above, where they're starting off hanging. And it's distance h off the ground, this being y equals 0. So that'll be our moment 1. And moment 2, let's just take the maximum height. So when little m has exhausted all of its kinetic energy and it's been given a total amount of gravitational potential energy. So this guy is going to have that final kinetic energy right as it's hitting, and little m is going to be a little bit higher up here, and the rope is scrunched, and it's going to have a velocity of 0. And the velocity here is what we found above for the big mass. All right, and so then I will call this here big H, and that's really what we were trying to solve for over here, was that maximum height. I'll call that big H here. So this is the ground, and this is y equals 0. So in the initial, we're going to have exactly the same thing. We're going to have the gravitational potential energy of each when they're hanging a distance h above the ground. And then afterwards, we do have kinetic energy of the big M block, and we have no kinetic energy, so we're taking a further out time for this small mass where it has used up all of its all of its kinetic energy and translated that to gravitational potential energy. So we have little m, g, big H, right? Big M is on the ground, so no gravitational potential energy for it, and little m has gone all the way until it's stopped and reached a maximum height, so no kinetic energy for it. And now we know what v squared is, so we can plug that in and solve for h, right? So we have GH, let's see, GH m plus m on the left side. Then we have, we're going to be plugging in this. I got to make sure I don't make any mistakes, so I'm going to go ahead and write it all out. M plus m, but there should be some things that cancel. In fact, we had a 2 on top and m bottom because we have a half and we're plugging in a 2, so those go away. M, G, H, and then, yeah, the rest of v squared is the masses there. All right. And then we have this other term, plus m, g, big H, right? Okay, so how can we solve this? How can we make this nicer? Well, you can see there's a g in every term, so the g can go away, right? G goes away. So this is really h m plus m minus m h, big M minus little m, over big M plus little m, and then equals little m h. All right. Let's see. So now let's get a common denominator. Yeah, let's get a common denominator here. So we'll multiply the first term by m plus little m over m plus little m, right? So that way we have h times m plus little m squared, and it's going to be all over m plus little m, minus big M times H times M minus little m, big M plus little m. We have this MH over here, this pesky little MH. Let's see. We can multiply this out and see if anything cancels. Looks like things might cancel here. That's why I'm pushing on. So we have H M squared plus 2 big M little m plus m squared minus m squared H minus, plus big M little m all over big M plus little m equals mh. Let's see, so this h is going to go here, then there, right? And we're going to have this this term cancel with this term, which is nice. And this term is going to add to the other one to make it 3. So we have, oh, I forgot to apply my h here. There's an h, oops, little m, h for that one as well. All right, so we have 3 big M, little m, h plus h m squared over big M plus little m equals little m times h. Wonderfully, we can pull out a little m here. We can pull out a little m and an h from the top. So we can do m, which cancels. I guess maybe we could just say, instead of having to pull it out, this cancels with one of those and that guy. And we can pull out an h. So we have h times 3 big M plus little m over big M plus little m. And that is equal to our max height. That's pretty nice. I think we actually did get there. That's a pretty simple, tidy result. All right, and if you plug this in, which we could have plugged this in earlier, but if you plug this all in, then you should get 1.46 meters. And instead of going and calculating that, I would like to see if this can be made to match that, because that seems more satisfying to me. And it looks like it's pretty darn close, actually. So we have here h times m minus m over m plus m. And then we have plus 2. So plus, let's get common denominator. So 2 m plus little m over m plus little m. Let's do this. Okay, so now we have common denominator. So we have an h out front. Then we have big M minus little m plus 2 big M plus 2 little m. All right. And common denominator, big M plus little m. I think this is working out. So this is going to cancel with that guy. And this is going to add to that guy. Can you see it? So h times 3 big M plus a single little m over big M plus little m. And that does indeed match what we got. So that is our y max. And should be the same, and it is. So energy is easier. Maybe this looks like about the same amount of work, but that's only because I kind of am obsessed with simplifying things. So way back at, way back at like this point, you could have just kind of thrown everything over and solved, right? Or maybe this point. But that is pretty nasty to plug into the calculator. But, you know, you can turn this term into a number and turn this term into a number before you added all that. Whoops. And it would have been too bad. So, so yeah, energy is easier. I think you would agree here. Energy was slightly easier. And in fact, quite satisfying that we got the two final answers in symbolic form to match. So, cool. If you enjoyed it, let me know. If you have a problem you'd want me to do and want to suggest, throw it in the comments.